thank you very much. It's great to be here. So I would like to talk a bit about the research we've been doing with me and my collaborators over the last few years on a style of software that we call local first software, which I'll explain in a moment, and also an open source implementation, a library that allows you to build this type of software called Automerge. So the background of this is web apps, basically. And so you will be familiar with the traditional form of building web apps, which is like, if you think the sort of early 2000s era, the web server would send some HTML to the client being the web browser. The web browser would render that HTML, the user types some stuff into a form, makes an HTML form post, HTTP form post back to the server, and the server sends back some more HTML to render the next page. And as you know, very few web apps actually still work this way nowadays. Nowadays, we've decided that actually it's too clunky to reload the entire page every single time. People developed single-page web apps, which means that there's a huge gob of JavaScript sitting on the client side, and actually the UI is typically being rendered by that JavaScript. When the JavaScript wants some data from the server, it queries a REST API. If it wants to save some data to the server, it posts it to a REST API. And otherwise, a lot of the interaction just happens in the web browser. And now this has enabled a really excellent set of real-time collaborative applications like Google Docs or Figma or the web-based versions of Microsoft Office and so on, which allow you to have several people editing a document at the same time. You can see other users' cursors, and as they type something, it appears immediately on other people's screens. All of that is super convenient, and it's enabled by this kind of architecture of having a big client-side app. However, there are also some big problems with this way of building web apps, and one of them is just simply the complexity of it. So let's think of all the layers that are involved in actually building this kind of rich, real-time collaborative piece of software. On the client side, what the browser is rendering is the content of the HTML DOM, representing the current contents of the page, and that DOM is manipulated by some JavaScript. So you've got some JavaScript which maintains its own state of the application and then uses maybe React or something else to render itself into the DOM. But then if you want to store some data, well, that storage has to be on the server, and so the JavaScript has got to talk via a REST API in order to contact the server and store the data there. So the JavaScript has got to convert its own state into an HTTP request, and it's got to take the response that it receives and turn it back into JavaScript application state. But now, on the server side, well, that REST API has to be implemented somehow, and most likely you will have some sort of server-side framework in which you've got some model objects representing the current state of the application from the server's point of view. These model objects may be written in a different programming language from the front end, or it might be JavaScript as well, but either way, it's probably a separate implementation that takes these HTTP requests incoming through the REST API, converts them into some in-memory state, and then if you want to save that, well, it's somehow got to convert these back-end side model objects into some data that can be represented in a database, for example, using an object relational mapper to store that data into a SQL database. And the SQL database then is some way of essentially giving you a data model on top of some persistent storage. And if you think about it, this is just complete insanity. We've got 6 different representations of the same information spread across client and server, and huge amounts of code are devoted purely to converting data from one representation into another representation, and are otherwise doing very little of value. And if you think about it, this is really not, if you were just starting with a clean room architectural implementation today, I'm sure this is not what you would design as a sensible, sane way of implementing software. So that is one problem. Let's talk about another problem in the current way how we build web apps. And that is to do with timing. And so let's say you've got some nice user interface, including a button, and when the user presses that button, some data should be stored on the server, or maybe some data should be queried. And so what happens is you've got some JavaScript code that registers an event handler on that button, and when the user clicks the button, that JavaScript code fires, and maybe that sends some HTTP request over the internet. And then on the backend server, well, there will be some API that handles that. It'll maybe talk to a database. blah, 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 etc. And at some point, well, the response will go back to the client. But what is the client doing in the meantime? Well, the client is probably showing a spinner, and it's spinning and spinning and spinning and spinning. And at some point then, finally, the response comes back from the server, and it'll fire some JavaScript code to handle the response, and then it updates the user interface to say, OK, thumbs up, everything is fine. OK, we stored the data on the server. Now, this is kind of painful because you're waiting for this really slow round trip to take place, and that spinner is kind of annoying. So people came up with this genius idea of, let's actually not show the spinner. Let's just show OK immediately. And that makes the user interface feel so much more live and interactive and responsive because you click the button and it immediately says OK. And we can call this optimistic UI. And this works fine as long as your HTTP request is reliable. The problem is just what happens if you send this HTTP request and the user is actually on some unreliable coffee shop Wi-Fi, or maybe they're on a train, going through a tunnel, and who knows, maybe the HTTP request got through, maybe it didn't, maybe the response got lost. We don't really know. At some point, the request times out. And now the application is in this awkward situation where it's saying, well, we already said it was OK in the user interface, and now we have to kind of tread back and say, oh, actually, sorry, it wasn't OK. After all, your data didn't get saved. We're not quite sure what state the system is in. Somehow wave up our hands and say there's an error. And this is not really great either. So this is, again, not really how you would design software if you were building it from scratch nowadays. So let's think about a better way of building this type of web applications. And this is really the core idea of local first software, which is an idea that we published, my collaborators and I published in this article. You see the URL here on the bottom a couple of years ago. We tried to articulate this idea that had been going around our heads for a while. And in that article, we tried to nail down the idea. I won't go through the whole details of the article. You can read it if you like. But I will just give you the core premise of it. And that is that in the traditional way of building web apps, really the server's data storage is all that matters. The client it's assumed not really to have any data storage at all. The client is just a web browser. It's essentially stateless. And that means if you want to store some data, if it hasn't been stored on the server, effectively it didn't happen. So the server is the primary storage for all data, and the client is, at best, a cache. And this is the traditional web app model. And what we're saying in local first software is, let's try to invert that model and say, actually, no, we can have persistent storage on the client. Why not? The client, even if it's a mobile phone or if it's a web browser, there is now persistent storage in those things. And the primary data storage is now going to be our client-side storage. And then a server still exists, but it's really just a backup mechanism so that if you lose your client, the server storage is still there. And it's a data synchronization mechanism so that if you want to access the data from multiple devices, well, the server is a convenient way for getting the data from one device to another. But what matters is the client storage, and the server storage is secondary. And so this is, it might just seem like a trivial change in perspective, but it turns out that if you adopt this change in perspective, it really fundamentally changes the relationship between the client and the server, and therefore fundamentally changes the type of software architecture that we can build. So going back to this example where the user clicks a button, in a local first model, in the first instance, the data would only be stored locally on the user's own device. And that is going to be fast, and it's not going to fail, because there's no network between the user and their storage. So the user can just store some data in the local device, and the event handler, as soon as it's stored it locally, can update the user interface saying, yes, it's OK. And this will be true. It really has been stored. And then in the background, there is a data synchronization process which will take any data that has been written to local storage, and it syncs it to a server. And if any data has changed on the server, maybe because another user updated it, that sync protocol will also bring it to the client and also re-render the user interface in order to reflect those changes that have happened. The key thing is that this synchronization protocol is now a background process, and the user interface doesn't need to wait for it. Now, moreover, in terms of this pile of complexity that we have with current web app development, let me point out that in this model here, there are some parts of the system that you would implement yourself, and some which are just off-the-shelf software. So the HTML DOM in the web browser, that's just off-the-shelf software. You don't write your own web browser typically. And likewise, the database and its persistent storage, that's typically off-the-shelf software. You just use Postgres or MySQL or whatever you like as your database. You probably won't implement your own database. But all of the layers in between are stuff that you would implement yourself. So like your JavaScript application state, your server-side model objects, your conversion to and from the REST API data model. Those are things you would have to implement yourself. With the local first model, one of the things that's really exciting there is that we can just massively reduce the number of layers that you have to write yourself. Because this data synchronization and storage layer that I talked about, so writing some data to local storage on the client and then syncing it with the server in the background, all of that storage and synchronization is generic code which you can just use an existing open source implementation, and you don't have to implement that stuff yourself. So the only parts that you would have to implement yourself is now actually this client-side application state that talks to the rendering, talks to the HTML DOM for rendering purposes of the UI, and it talks to this open source framework for storage and synchronization. And that is it. You don't have to write your own backend. And this is really crucial because if you don't have to write your own backend, that means you don't have to operate your own backend. You don't need a 24/7 team of people who carry pages and are willing to be woken up at 3 in the morning because your backend has gone down. Because the backend still exists, but you can outsource it to some company that enjoys running backends. And so this is at least the theory. This is the vision for the future. At the moment, this is not yet really fully realized because it's still only just coming out of research. But what I want is, for the coming years, for local first software to be commoditized in such a way that essentially you can focus just on writing the client-side logic, and then the syncing service is just an off-the-shelf service that you can just subscribe to something for cheap, and somebody else will run that for you. So comparing the traditional model of cloud software to this vision of local first software that I've articulated, there are a couple of key differences that come to mind. One is in terms of real-time collaboration. So if you want Google Docs style, as one user types something, the other user immediately sees it, you can implement that with cloud services and your own REST APIs and so on, but it's quite hard work. There's a lot of specialist libraries you need to use. A lot of the web frameworks don't really have good support for this type of data exchange. The web framework will say, here's a WebSocket. Have fun with the WebSocket. Figure out how to use it yourself. You have to do a huge amount of lifting yourself in order to actually get something approximating real-time collaboration. Whereas in local first software, the data synchronization process, that can be real-time, and the process for updating the user interface based on changes happening, that needs to be there anyway. And so it's actually much easier to implement this type of real-time collaboration in the local first model. Another big difference is offline support. If you're relying on a server as your primary data storage and you can't reach the server because you're on a train going through a tunnel, then, well, your software just does not work offline. The user can't continue working while they are disconnected from the internet. Whereas if your data storage is local on the user's own device, yes, the user can continue working, and when they come back online, well, the data sync protocol will just pick up and sync all the work that the user has done in the meantime while they were offline. And so local first software makes it just so much easier to make software that works offline. The next problem with cloud software is from the user's point of view. If the user invests years of their life in using your app to write some documents or whatever the work they are doing, and then the cloud service shuts down because it's an early stage startup that runs out of money, or because Google decides that you have violated the terms of service and they're going to lock you out of your account, you lose all of the data because you don't have a copy of the data on your own device. All of your data storage is on the cloud. If you lose access to that cloud account, all of your data is gone, and that is really terrible from a user's point of view. At least with local first software, there's some software running on your own device, and the data storage is on your own device. So even if you get locked out of any cloud service that is being used, you still got at least a copy of the data there locally, and you can continue using that. And then finally, what I said earlier, with this cloud software, you have to run your own backend because the backend runs your own application code, and that means you have all of the overheads of having a back-end team, and having people on call, and so on. And it's just really expensive. Whereas with local-first software, the syncing service is just a generic piece of infrastructure, just like a database that you wouldn't write that yourself. You would just use an off-the-shelf piece of software. Now, I want to be realistic here, and I don't want to say that local-first software is amazing and it's great for everything. I think there are certain applications, certain types of software for which it's a good fit, and others for which it's not a good fit. And so I want to just be totally clear and open on where I think those strengths and weaknesses lie. Where I feel local-first software is a good fit is things that I think of as file editing. So in a traditional desktop software point of view, it would be the type of software where you open it up in a piece of software, you open up some file on your file system, you edit it, you save it again afterwards. And that applies to a fairly large class of software. It's text editors and word processors, but it's also spreadsheets and slides for presentations, it's vector graphics and bitmap graphics, it's video editing, it's music editing, it's CAD software for engineering, so like building electric circuits and so on. All of those types of software fit really well with the local-first model, where it's just the user has some data that the user themselves created, and the user wants to edit that data in whatever way they want. Another type of software where local-first works well is, broadly speaking, productivity software. And what I mean with that is sort of note-taking, to-do apps, issue trackers, and those types of software where it's a team collaborating on something. But again, it's essentially user-created data that the user wants to be able to update in whatever way they like. The places where local-first does not fit well is primarily where there's some sort of real-world resource involved. And so, for example, if it's a bank account, well, the bank maintains the authoritative state of that bank account. And if the user edits the state of their bank account to add an extra zero to their account balance, the bank is not going to be interested in that because your bank account is not a collaboratively editable document, right? The user's edits to this data are of no interest to the bank because it doesn't change how much money you actually have in your account. Likewise, if it's like physical inventory, the objects on a shelf are not going to be affected by some edit that a user makes to some file. And so for these types of software, there's naturally an authority that maintains the primary copy of the data. And for that, it's best to just use a traditional cloud service, keep things as they are. Local-first is not a good fit for this type of software. So local-first is basically good for the types of software where the user can edit the data in whatever way they like. OK, let's make this practical. So far, it's all been kind of highfalutin ideas. So let's talk about a real implementation that you can use in order to actually build local-first software if you want to experiment with this. And so in particular, I want to talk about this library called Automerge, which I and my colleagues have been working on for several years. And what it does is it provides you essentially a JSON-like data model. You can think of it a bit like a client-side database, an in-memory database that allows the client to maintain the state of some application and to update that state. And any updates that you make are synced to any other users who also have a copy of that data. And so let's take as an example a to-do list. And imagine this is a to-do list that is synced between you and your colleagues, or between you and your partner, or so across multiple devices. And so you could represent a to-do list, for example, as this kind of JSON document here. So I've got 2 items on this to-do list: buy milk and water the plants. And for each item, there is a flag called done, which indicates whether you've checked the box or not on whether it has been done or not. OK, super minimalist, but it'll get the idea across. And the way you can update this, this to-do list now is using this JavaScript API. There are also APIs in other languages, but I'll just show the JavaScript version. And the idea is you have this let's say you want to update the value of one of these done fields to true because the user has pressed the checkbox, and now you want to reflect that state in this updated JSON document. And so let's say that watering the plants has been done, and so this done field wants to be updated from false to true. And the way you would do that is in the JavaScript down here, you have this doc.todos, square brackets 1, .done equals true. Just a very straightforward, mutable API for modifying the text, modifying this JSON document. This Automerge API, though, works with this function called automerge.change, and the idea is that you pass in the current state of the JSON document and you get back a new state, and so it's actually immutable, even though it's using this mutable API internally. What's happening here is this is actually a JavaScript proxy object that intercepts any mutations that are made and records exactly what was changed so that it can propagate those changes to any other users who also have a copy of this to-do list, and so that it can then merge any changes from different users together. So you pass in the current state, you get back a new state. When you call automerge.change, you can also attach optionally, if you want, a human-readable message to this. You can think of this very much as like a commit message in a Git repository. So you make some change, and then you add a descriptive message describing what has changed. That message has no effect on the actual behavior of the library. That's only if you then later want to go back and inspect what has changed over time. You can look at the edit history, and those messages, those human-readable messages, might be useful to you then. And then inside this callback, as I said, you have this mutation API that you can use to describe in what way you want this JSON object to change. So this is one way how you might update the document, by setting the done field to true. Another thing that you might do to the same document is to add a new item to the to-do list. And in this case, let's say here I need to do the laundry, and so I'm going to do doc.todos.push this JavaScript object here, and this is going to add a new item to this to-dos array. So todos.push is just the JavaScript API for appending an item to the end of an array, and that causes this new item to be added here. So hopefully this is all pretty straightforward. It's just, as you would expect JSON object manipulations to behave. Now, what makes Automerge interesting is that these objects are stored locally on your own device, but there's also this sync protocol that syncs any changes with a server and with other users. And so this means now you might have multiple users which start off with the same document, and user A updates the document to set watering the plants to be done, and independently on a different device, a different user, B, updates the to-do list to add do laundry to this. And so now you've got this kind of divergence. You can think of it in Git terms like commits happening on two separate branches, and these branches then need to be merged back together again. And so in Git, well, this kind of merge, if you've got these merges happening close together, this would probably be a manual merge conflict that you would have to resolve. But with Automerge, what we wanted is that in as many cases as possible, there's no manual conflict resolution, but rather it should merge these things automatically, hence the name Automerge. And so what Automerge does is when these two users run the sync protocol and they exchange their modifications to this, well, we merge it together in the way you would probably expect, which is the watering plants is still done, and the item to do the laundry has been added to the list. And these things can be merged cleanly because they're updating different objects, and so there's no problem in merging these, really. And in general, any type of updates that the users might make concurrently can always be merged by Automerge automatically. There's only one case that can't really be handled, and that is if multiple users independently update the same key within the same object. And in that case, Automerge doesn't know which of those values it should choose. It chooses one of them arbitrarily to be the default value, but it keeps all of the different values that the users have set. And so then if you want a conflict resolution user interface that allows the user to choose which of these values they actually wanted, you can have that. But if it's not that important, so for example, if it's, say, a graphics application where a box could have this XY coordinate or that XY coordinate, different users might drag the same box to different positions, but maybe which exact position it's in doesn't matter too much as long as all users end up with the same state. And in that case, you might just choose to pick one of the XY positions arbitrarily. But in general, it is possible also to do this manual conflict resolution if multiple users update the same value in the same object. But that's really the only case that needs to be handled automatically, and everything else, which is like inserting and deleting items from lists, updating keys in a map, or also deleting keys, and we're increasingly adding other types of operations as well. They can be merged automatically. Another type of edit that Automerge can merge automatically is text editing. And so this is coming back to the Google Docs style example again. You can imagine users having a text. Both users start off with the same text, hello, exclamation mark. And the red user at the top edits the text by inserting the word world before the exclamation mark. And concurrently, on a different branch, the blue user at the bottom inserts a smiley face after the exclamation mark. And again, these edits might happen offline, but when the users come back online, they run the sync protocol, they exchange their edits, and we want everyone to end up in the same state, and we want no edits to be lost in this process. And again, Automerge will handle this automatically in the way you would hopefully expect. So that is, we have the word world before the exclamation mark and the smiley face after the exclamation mark, which seems like the most sensible way of merging these edits together. And so that's really the general idea of what Automerge can do. The way this is done is, in research, we call this a conflict-free replicated data type, or CRDT for short. And this is essentially a family of data structures that allow these kind of concurrent updates by different users and which provide built-in algorithms for merging them back together again. And the properties that this merge provides us is that, well, if multiple edits happen, we try to preserve all of those edits as much as possible. We try to not throw away any user input. But if two different users have seen the same edits, then they must be in the same state, even if they actually saw the edits in a different order. So I first saw my edits and then saw my colleague's edits later, whereas my colleague first saw their own edits and they saw my edits later. And nevertheless, no matter in which order we see each other's edits, everyone should end up in the same state. You can have branching and merging very much like in Git, except rather than this manual conflict resolution, we have automatic merging as much as possible, as I explained. And one thing which is quite exciting, which we are increasingly working on, is actually allowing this kind of branching and merging to be exposed to users as well. And so we, for example, got an experimental text editor, which we called Upwelling, which allows you to essentially do like a pull request for a rich text document. So the idea is then that you might have a user goes off on a branch, makes a bunch of suggested edits to a document, and then does a sort of pull request-like thing, asking their coworkers to review the edits that they've made and merge it in if they like. And you could imagine doing a similar thing for graphics software or for spreadsheets also. Why do we not have this kind of suggestion workflow that, as software developers, we use Git and we use these pull requests as ways of being able to review each other's work and merge it in when it's ready? Really, we should be trying to integrate those similar kind of branching and merging and diffing and version control features into all sorts of different types of application software. And that's where we're trying to go with Automerge. OK, so the way Automerge is implemented is as a Rust library. And you can use it through a Rust API if you like. But the idea is that Rust is super portable. And so, for example, we can compile it to WebAssembly and then have a JavaScript and TypeScript wrapper around it. So you can use that for building web apps, for example. But we can also have a C API, and that's used for having bindings to other languages, such as Go. There's a Swift API so that you can build iOS apps. There's a Java API, which you can use to build Android apps. And the idea is that you can then have a cross-platform apps that run on all of the platforms, and they can all interoperate with each other because they all speak the same data model, data format, and they all speak the same sync protocol for exchanging edits with each other. However, Automerge is really just an in-memory data structure library. And so for any I/O to happen, so if you want to actually persist the data or if you want to send it over network, there's a separate companion library called Automerge repo, which handles the storage and networking. And so in particular, storage could be different things depending on which platform you're running in. If you're in a web browser, you might be using IndexedDB. If you're in a file system, in Node, you might be writing to the local file system. If you're on a mobile OS, you might be using the storage APIs provided by that OS. And so this is pluggable then. You can just use whatever storage is available on the platform that you're on. And likewise for networking, if you want to go via a WebSocket server, that's fine. If you want to sync via peer-to-peer via WebRTC connection, that's fine. If you want to use a plain TCP connection, that's fine. Really, any kind of way of getting the updates from one user to another will work with Automerge. A little bit of history of how this library came to be. So I started working on it in maybe 2017 or so. And for the first couple of years, it was very much a research prototype. So it had extremely bad performance, extremely high memory use, and extremely large file sizes. But it allowed us to work out, like, what sort of APIs do we like? What is the programming model? How do you build applications on top of this kind of substrate? And then in the last few years, we've increasingly productionized and professionalized this project. And so in the version 1.0, we introduced a compressed data format, a binary data format, which has vastly smaller file sizes than what the previous versions of Automerge had. And we introduced a new synchronization protocol. In version 2, we moved from a JavaScript implementation to a Rust implementation. And as part of that, performance increased massively. We've been investing much more in performance. And we've now got one person working full-time, funded by the community, to do software engineering on this project, and several other members of the community who are contributing a lot to the project. So it's no longer just like me hacking on this weird academic prototype, but it's actually now production quality software, and commercial support is available should you want to put it into production apps. And the version 2.1, which should be coming out roughly any time now, adds a few interesting features. So in particular, it adds support for rich text, that is text with formatting. So this sort of idea of Google Docs is moving ever closer. But you can use it for all sorts of other types of applications as well. 2.1 adds support for Automerge repo, the storage and networking library that I mentioned, and further performance improvements. OK, so I thought in the last section of this talk, I might just give you one particular example of the merging algorithms that we've considered. And I thought I would talk a little bit about rich text, since that's a new feature. And it sort of exemplifies the types of problems that occur when you've got multiple users concurrently editing some data. And the algorithm I'll talk about is something that we published in this article in 2021. Peritext is the name of the algorithm. And the idea is really to answer the question, how do we best represent text with formatting in such a way that multiple users can update it independently from each other, and we can merge those edits together in a way that makes sense. And if you're thinking about how do you represent rich text, well, your first instinct might be to represent it as a tree, because the HTML DOM is a tree, and so why don't we just adopt the same data representation? So we could have, in this example here, we have a text document consisting of just a single paragraph with the text, "The fox jumped." And let's say that user A wants to make the word jumped bold, and user B wants to make the word jumped italic. And those two edits happen concurrently, independently from each other on two different devices. And now we want to ask, well, what happens when we sync these things up and we merge them together? And there are CRDTs for tree data structures that you could use for this kind of thing. And the way they would work is they say, well, you added a bold node, and you moved the text jumped into that bold node. And you also added an italic node, and you moved the text jumped into the italic node. So I'm going to preserve the fact that you added both a bold node and an italic node. And we're going to have the text jumped in each of those nodes. And the result is now that the word jumped has become duplicated. The text is now the fox bold jumped, italic jumped. And that's kind of weird. We don't really want that. We changed only the formatting. We did not want any text to be duplicated. So it seems like representing the data as a tree is not really the right way of doing it. Let's try an alternative. Let's try representing the data as markup instead. So we could have text with some inline characters that tell us this is the beginning of a bold span, and this is the end of a bold span. And so it could be like literally HTML with angle brackets, or you could imagine some sort of special marker characters that are embedded in the string in some way. Whatever way you do it, let's say that the user A on the top wants to edit this document and unbold the first three words of this text so that it's now just totally non-bold, the fox jumped over the dog. Whereas user B wants to unbold only the word fox. And so the way you would implement the unbolding everything is by removing the two bold characters, so the start bold and the end bold marker. The way you would unbold just a single word is by inserting an end bold before fox and a start bold after fox. What happens when we merge these things together now? Well, it's kind of messy, because the two originally green markers, so the start bold at the start of the string and the end bold after jumped, those two have been deleted by user A. Whereas user B has inserted two new things, an end bold before Fox and a start bold after Fox. So now we have an end bold before a start bold in the final merge document, which that's kind of weird, but OK, we could ignore that. But now we have a start bold before jumped, and now the entire rest of the document has become bold. And that's really weird as well, because the user was just changing some formatting on the first few words of the document. Why has now the entire rest of the document become bold? This is really weird behavior, and we think this is really not good behavior either. So this means representing data, the rich text as markup, does not seem to be a really good idea either. OK, let's try a third attempt. Let's try a really stupid way. Let's say every single character has a bold flag or non-bold flag attached to it. And we'll just store that independently for every single character. And OK, that's probably going to be inefficient, but maybe we can find ways of compressing the data. Whatever way, just assume for now that we are just going to attach the formatting to every single character. And so in this case, if jumped is bold, we're just going to have a bold flagged on the J, a bold flagged on the U, a bold flag on the M, and so on. OK, now, besides bold and italic, one thing that we want rich text to be able to represent is comments. Because, like in Google Docs, you can mark some text, select some text, and then put a comment in the sidebar. And we want that kind of thing as well. So let's say, for example, you attach the comment also to each individual character. So let's say here, the user A wants to ask the question, which Fox, and attach this comment to the first two words of the document. Concurrently, the user B wants to insert the word brown before Fox. Now, what happens when we merge these things? Well, now, when the user B typed brown, there was no comment attached to the characters of brown. And so therefore, the merged state will now have the comment split into two separate spans, where the and Fox have comment attached to it, but the word brown has no comment attached to it, because there was no comment there at the time when those characters were inserted. And this is kind of messy as well. OK, we could kind of try to maybe patch over it by closing the gap. But now the algorithm gets quite fiddly, and we have to convince ourselves that it's actually correct. And there are other edge cases also, which I don't have time to talk about, which are kind of annoying. And so just overall, it seems like this approach of attaching per character properties is not really great either. And so this finally brings us to the approach that we adopted for Peritext. And this approach actually seems to work quite well, finally. So this is the fourth attempt, and it works like this. We just have the text, the plain text, with no embedded stuff, just as a flat string. And then separately, outside of the text, we can attach annotations to spans of text and say, from this character up to this character is bold. And let's say we start off with this document here where A and B start off in the same state. And we're just going to say the whole document is bold for now. And crucially, we're going to attach a timestamp to that bolding operation. And we're saying this span of text was marked bold at a particular point in time. Now, let's say that the user A then decides to unbold the second and third word of this text. So the remains bold, and Fox jumped is unbold. And the way we do this is we do not change the fact that it used to be previously bold. So the T1 bold span remains there. We don't delete it. But we add an additional formatting annotation saying Fox and jumped are now unbold, and we have a timestamp T2 on that. And T2 happened later, so T2 is greater than T1. And this tells us that for the second and third word of the text, the unbold overrides the previous bold. And this now gives us this kind of temporal ordering that we needed in order to figure out what happens when multiple things happen concurrently. Let's say on user B decided to mark the third word, jumped, as italic, and that has a timestamp of T3 on this operation. And now we can finally merge those things in a sensible way. Because the way we merge is we just keep all of the annotations that have been created. We don't delete the annotations ever. And this is fine because the number of formatting annotations in a typical text will not actually be that great. And so it's fine to just store them forever. And in this case, we know that the must be bold because it was once bolded and never unbolded. The word Fox must be unbold because it was first bolded and then unbolded by T2, which is greater than T1. And the word jumped must be non-bold because it was unbolded by T2 and it was italicized by T3. And so this finally gives us a good algorithm for merging these rich text edits together. And that's really all that I have time to talk about today. So that is the view of Automerge. This rich text algorithm is now implemented as part of Automerge, and we're also adding bindings to text editors like ProseMirror, for example, which allow you to actually build collaboration software, including these rich text features. But you can build many other types of data on top of this general purpose JSON model as well. And if you're interested in any more of that, there's details on the Automerge website, various academic publications that I've worked on over the years which describe various algorithms that go into this, and a huge thank you to the members of the Automerge community who've put a huge amount of work into actually implementing these things in practice over the last years.